Greetings and welcome to another lecture in Introductory Psychology. This one is on the scientific method, which actually is not just for psychology, it's applicable for any kind of science that you care to mention. It has many steps to it. I'm simplifying it here. The other thing you need to realize about science is that this list that I'm going to give you has a discrete beginning and a middle and an end. But science is not a straight line. Science is a loop. Because what we have learned before feeds into what we're studying tomorrow, and it simply never ends. But we have to start somewhere. So these are the steps that go into the scientific method. The first step is to see something that's interesting. Seriously, that's the first step. It all begins with curiosity. You see something and you want to know why that happens, or when it happens, or how it happens. You want to know anything, really. So you see something that's interesting. Now, the first thing that you want to do once you see something that's interesting, let's stick with behavior. You see a behavior that's interesting. First thing you want to do is look it up. Now, you don't just want to go to Google and Google it. That is not sufficient. Even Google Scholar is not necessarily sufficient, because you may have to go into the dim mists of antiquity when knowledge was kept in books and not on computers. But you want to learn everything you can about the topic. First of all, to make sure that someone else hasn't answered your question first, because you really don't need to go through all of this work if someone else has answered it and it's been replicated enough times to be thought to be accurate. More about that later. But you also, in case someone hasn't answered your question, you want to learn everything about it and everything about anything related to it, so that you know how to ask your question. You know how to research this. You know how to, figure out the best way to answer this question, what technique you're going to use, what subjects you want to use, how long to do it for, that sort of thing. Once you've learned everything you can about your particular question, you want to put it into words. Don't just, and they have to be very precise words. It's often best to come up with something, you want to study, so you can't come up with something vague. You need to come up with something precise. Specifically, once you have this question, you want to come up with something called a hypothesis. Now, a hypothesis in science is a testable prediction. So make a prediction. I predict that in these circumstances, this will happen. I predict that under these particular manipulations, this will happen. I predict that this group will behave differently than this group under this manipulation, whatever. Okay? But it has to be something that is testable. I mean, there are lots of predictions out there that are not testable. For instance, this is where God sometimes makes an appearance. Unfortunately, we cannot prove or disprove scientifically the existence of any sort of supreme being or beings. And so therefore, as part of your hypothesis, you simply cannot say, well, this is true because God makes it so, because you cannot scientifically test God. Or at least no one has come up with a way to do it. So it needs to be something that is indeed scientifically testable. Something you could go in. I mean, the classic example of this in terms of medicine is, I predict that if I give people this medication, this will happen. That's testable. It's a prediction. It's a hypothesis. And this has to be testable because, of course, the first thing you're going to do once you come up with your hypothesis is test it. So you're going to run the experiment. You're going to run the research. You're going to run the correlational study. And you'll learn all about these in roughly the same section. But you need to test the hypothesis. Now, your hypothesis then, once you've tested it, is either going to be supported, that the research you found did indeed support your hypothesis. It does appear you're on the right track. Or it will not be supported. And that's usually how scientists say it. Scientists don't talk about proof. Proof is almost impossible in science. For one thing, you cannot prove that something does not exist. Okay? Because, after all, maybe you're just not testing it under the correct circumstances. But it can also be difficult to prove that something exists or that something works this way instead of that way or whatever. Scientists rarely use the word proof. Because, quite frankly, someone could come along tomorrow and come up with research that basically will cause you to have to throw your proof into the trash can. Happens all the time. Okay? Oh, boy, my goodness. Physics, for instance, classic example. is that people used to think they knew how gravity worked. Isaac Newton and the apple falling on his head and other apocryphal stories. And then along came Albert Einstein, who came up with entirely new ways to explain what we all see, what we all know happens. And the interesting thing is, once they figured out ways to actually test Einstein's predictions, some of them we still don't know how to test, okay? But some of the things that we came up, we could only test years after he came up with them. And it turns out that he seems to be right. His work is supported. So what happened with everything we knew about gravity before Einstein? We kind of chucked it out. Although sometimes these things also come back to haunt us. Classic example in biology are various theories of evolution. One of which, for instance, came up with a fellow by the name of Lamarck. And Lamarck believed that characteristics that individual creatures develop in their lifetime can be passed on to their offspring. For instance, classic example for Lamarck is he said that giraffes have long necks because they would stretch their necks, and as they stretched their necks got longer, and these longer necks were inherited by their offspring. Or for instance, if a person became a bodybuilder, then their children would be naturally more muscly. And when Darwinian evolution and the various variations on it came along, people more or less said, no, 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 you cannot pass on acquired characteristics. Except now we're finding that maybe you can. It's the delightful thing about science, is that even when your hypothesis is supported, it doesn't necessarily mean it's true. More about that later. Once you've drawn your conclusions, your hypothesis is supported or it's not supported, you need to tell people what you found, even if you didn't find anything. This is something that a lot of graduate students, for instance, agonize over. Oh my God, I did this thesis, I did this dissertation, and I didn't find what I expected to find. Oh my God. Well, the thing is, that's okay. Because now we know what it isn't. It's not that, so we know what it's not. And knowing what something isn't is pretty much as useful as knowing what something is, because now we know where not to go. We know what not to look at to get the answer. So you want to report the results, whether or not your hypothesis is supported or whether it's been unsupported. Now, usually we wind up reporting these in scientific journals. Because scientific journals go through a huge approval process. You think writing papers in college is tricky. When you do research and you have to hand that paper in and you send it to a journal, the journal will then send that paper to up to half a dozen or sometimes more other scientists who will go over it with a fine-tooth comb and make sure you didn't make any mistakes. You didn't make any mistakes in the method. You didn't make any mistakes in the analysis. You didn't make any mistakes in your statistics. You didn't make any mistakes, period. Because if you made a mistake or you didn't look at something they think you should have, they will send it back to you and say, fix it. And then you have to send it back. This is why scientific journals are called peer-approved, because they need to be approved by basically a jury of your peers. And once everybody has decided that yes, you did it right, and yes, it looks like your results, whatever they are actual, they accurately reflect the world, then and only then should it be published. Now, once these results are published, they're not only published in order for people to see what you did, they are also published to allow for replication. Replication is doing something over again. You've done it once, you need to do it again. Why? Because weird things can happen purely by chance. And it's possible that whatever research you've done does not accurately reflect the world, even though your statistics say that it should, or your method was perfectly consistent. It may be the results you got are just because something weird happens. Okay? Somebody comes up to you and says, give me a quarter. You give them a quarter. They flip the quarter, it comes up heads 10 times. What's the first thing you say? Well, if it wasn't your quarter, I'd say, give me that quarter, let me look at it. But the second thing you're going to say once they do this amazing thing is what? You're going to say, do it again. Because simply doing something once is not impressive. I have bowled like once in my life. But one of the times I hurled that ball down that alley, I knocked all the pins down. It never happened again, but if I had just worked on that one ball throwing down the alley, I think I was a damn good bowler. Replication is important. You have to do things again. And in a perfect world, results would not be publicized until after they have been replicated a few times. As you all know, we don't live in a perfect world. And these days results get reported when they have been found maybe once. This is why, if you follow science in the news, you would think that science basically is a bunch of crap. Because one day on the news, vitamin E helps prevent cancer. And the next day on the news, or 6 months later, no, it doesn't. And you're thinking, what the hell are these scientists smoking? Okay? What is going on? Well, what's going on is that initial report was made before researchers were allowed to replicate the findings, to make sure that the findings were actual and were not just some sort of weird chance thing happening. Replication is very important because if you don't replicate things, people, as I pointed out, they wind up losing confidence. Okay? Things need to be replicated before they know if they're accurate. Doesn't matter what your statistics say or how beautiful it is. It has to be replicated several times if possible, and not only by the person who did it but also by other people, okay, to make sure that it's not just some sort of bias or error creeping in. So let's say that it's been replicated. Let's say your hypothesis has been supported. What are you going to do? You're going to test it again. Not replication here, but for instance, maybe you tested that medication first on males. Well, you better test it on females. Males and females are very different in their biology, and they're very different in how medication can affect them. Maybe you tested it on adults, you want to test it on children. Maybe you tested it under these circumstances, you want to test it under that one. This is why science never stops, because we are never going to know the answer to everything. And if you've ever heard the cliche, the more you learn, the less you know, welcome to science, because for every question you think you've answered, 10 more will pop up. So what do? Well, when you're tweaking it, starting over again, you're probably going to maybe see something else interesting or come up with another question, and you're just going to work again. And eventually, you're going to build on or perhaps even create a theory. Now, the word theory does not mean in science what it means in English. In English, we tend to use the word theory meaning basically hypothesis. This is my theory. It's my educated guess. That's not a theory. That's a hypothesis. A theory is absolutely everything that we know about the topic over years, over centuries in some cases. That's a theory. It's not a guess. It's not a maybe this is so. In science, a theory is something that has been tested and tested and tested and tested and tested and shown to be accurate. Now, let's say, for instance, that you get a question from a theory. Oftentimes, theory should go at the beginning, because when you're doing the research, you find a theory. Like I said, it's circular. So let's say that you have this theory and you come up with a question and you test it and your results do not support the theory. Okay? Or they replicate it and it still doesn't support the theory. Now you can do a couple of things here. You could chuck the theory entirely, throw it out. Not usual, not good. Usually what happens is you tweak the theory. You change the theory. The theory has to include every bit of information that we have. You can't just go, well, it doesn't fit my theory, I'm going to throw it out. Okay? It has to fit everything. It has to fit all the information that we've learned, which means that theories are constantly changing. If you want something that never changes, that's called a law. And there are very few laws in science. There's a lot of theories and there's billions of hypotheses. Okay? So we have the theory, it's everything we know. We're going to test it again. We're going to research it. We're going to start it, and round and round and round and round we go. So when I start talking about different ways of doing research, or when you read about research in a newspaper or a magazine or online, then always think about this process that needs to be gone through. Science is complicated. Science takes a long time. Research is not something you do on a whim, but research is the way that we learn about the world. Very important stuff.